Okay, so now I'm Snell. So he starts with a quick primer on Y crystals, and that starts with a little discussion of the electromagnetic spectrum so that we can think about Y X-rays. So this is a picture of the electromagnetic spectrum, and as we go from left to right, the frequency goes up, the wavelength goes down, and we have names given to these various bands of the spectrum here. This is an interesting sidelight. It's not that much gets through the atmosphere. Tells you what you can see with the resolution offered by.
Can you try to switch up the
Yeah, thank you.
Go to the screen.
Yeah. So this tells the scale of the things that can be seen. And this is an interesting one. It represents the effective temperature at which the most intense radiation is emitted from a so-called black hole. This is the source of our understanding that the sun is 10 billion degrees or whatever it is. This is an area of interest, as we'll see. I think Eddie put this in to show that the process of interference of waves occurs at all length scales, and not just in the X-ray and light regimes. And here's a little hole in a screen, and here are interfering waves that came through it. This is the object of our affection. It's a beautiful protein crystal in a very clean environment. You won't see this very often. But crystals are characterized by sharp edges, flat faces, regular geometrical shapes. In extreme cases, extremely good ones, one can get incredible amounts of information from these crystals. So this is a protein, which he doesn't name in his slides, and therefore I don't know what it is, that diffracts at 0.9 angstrom resolution. Actually, it's 0.85. This one image has 5,000 data points in it, and the kind of resolution that is available there gives you maps like this. These are illustrations of difference maps. First of all, you can see how accurate the structure of these rings are, and you can really see the holes and everything. But difference maps, where this is a sigma, I presume, and gives you a view of weak density in the difference map, reveals hydrogens very clearly. So these crystals can really tell you a lot, especially when they diffract to extremely high resolution. This is a very favorable case. So the next question is why X-rays? This is Rankin. This is one of the earliest radiographs taken of a human hand. The early X-rays that we had were polychromatic, and it's been an important advance in crystallography to learn how to generate monochromatic X-rays. And there have been many steps in this over the history of the field. Yes. Well, I brought this one in, and the trouble is the battery seems to be, maybe it'll work. All right. So the earliest X-rays were generated by tubes, which were still in use when I came in as a graduate student, and in fact, one still sees them in laboratory sources. They involve a characteristic element in the target. These are the most familiar elements, and there are transition lines, usually in K or L shells, which come about when these elements are bombarded by a high-energy electron beam, and they emit radiation this wavelength. This is a picture of copper, the spectrum, wavelength, and angstroms. This is a peak line, the famous copper K alpha line. And there's a secondary one, copper K beta, and it was an object of concern when I was a student how one filtered out the K beta from the K alpha. Those generators were limited by the amount of heat that could be dissipated in a metal target, and a major advance in the field was the creation of a so-called rotating anode, in which you didn't have a fixed target. The target was a wheel like this that rotated at high speed, and the X-ray beam just impinged on one point here, and the amount of power that one could pump into it was correspondingly much higher. I might comment that today there are laboratory sources that use liquid targets, gallium, I think, and one can put in huge amounts of power compared to what you can put into a solid because it's already melted. This is a picture of a typical laboratory setup. Here is a detector. Here is the ionometer holding the crystal. This is a cooling jet. Here's the X-ray beam. And these things will look familiar. So that's where we stood before synchrotrons came into being. I had a big chance in my career that I completely blew about this. So I was an undergraduate physics major, and I went back to Harvard to visit my advisor, and they were using something called the Cambridge Electron Accelerator, which was running right there in the middle of the university. And he said to me, "This thing is putting out huge amounts of X-rays, and we have to block. Can you think of anything we could use them for?" And I said, blah, 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 blah. But of course, at that time, they didn't know that they were focused in the forward direction. It's a relativistic effect that they hadn't figured out yet. But I had my shot. Anyway, so this is a picture of the Crab Nebula in which electrons are accelerated by very energetic electrons interact with powerful magnetic fields, undergo strong accelerations, and they radiate in the X-ray region. And it's an example in the universe of synchrotron radiation, something we want to harness in the laboratory. Electrons radiate when they are accelerated. Accelerated means a change in velocity or a change in direction or both. So when you put an old-fashioned incandescent light bulb on, the electrons are bouncing around at random at high energy, and each time they change direction, it's an acceleration, and they radiate. Synchrotrons harness powerful magnets and the technology from particle physics to create storage rings around which electrons go. And at the corners of these rings, where the electron beam changes direction, there are magnets called bending magnets that bring them around the corner. And at this point, there's an acceleration, and the electrons emit radiation that's captured in this direction. In the middle of the straight section, and we'll see more of this later, people at a later time put in arrays of magnets that look like two combs facing one another. They're called insertion devices. They move the electrons back and forth. So even in the straight sections, one can now get X-ray emission. So the intensity that one can get from these synchrotron sources is actually amazing. This is a diagram which shows photon energy in electron volts, electron volts, I'm sorry. And so ones we use for crystallography are on the order of 10 keV, typically along here. So this is the problem with this thing. And the this is brilliance along the vertical axis, which is a measure of both how parallel the beam is and how small an area you can focus it into. And the numbers up here are 10 to the 18th or 10 to the 9th. And these are the best conventional sources that we have available. This is the picture of a synchrotron. Anybody know which one?
Yes.
Right. So those were, hang on, I missed a slide here. Where is it? Maybe it comes later, I'm sorry. There was one that shows the power of the X-ray laser system later. Okay, so this is the same slide again. I don't think I screwed up. These, all right, so here is the scale of the old conventional sources. And up here, 8 or 9 or 10 orders of magnitude are the LCLS, other sources, and they are.
Let me change your batteries. So what was the problem with that one?
It's too bright.
Well, is this one too bright also?
It's less
a little less.
I'll try to flip it. All right.
The on-off button is on the bottom there.
On the bottom.
Yeah.
That?
Yeah.
So this is, well, brilliance that's many, many, many log units ahead of what we have at synchrotrons today, and even next generation synchrotrons like the MSLS2. This is a picture of the Lattman coherent light source, which is the first really functional X-ray laser that was built at Stanford as part of the LCLS, as part of SSRL, sorry. And
Red button.
the red button.
Okay.
Let's see. How many pointers can I go through? So this is our first illustration of kind of organized electron motion to produce radiation. This is a magnetic field line. Electrons moving in this direction interact with magnetic fields to form a spiral. This is the kind of thing you see in electron lenses and electron microscopes. And these emit photons. Remember that the force exerted on an electron happens both perpendicular to the direction of its motion and perpendicular to the magnetic field. It's a source of the so-called right-hand rule that you learned in elementary physics, at least that you met in elementary physics. So this represents a strong way of producing radiation. This is a section where he goes through the parts of the LCLS that I'm going to go through quite quickly. This is the injector. This is the electron accelerator system, microwave cavities. This is the steering section that organizes the beam and trims it. And this is the sophisticated version of magnetic arrangements that produces the X-rays and the X-ray lasers. So the X-ray beam will come in through, the electron beam will come in through this gap. These are paired magnets, north-south, the next one is south-north, north-south, south-north. Here's a picture of how they're organized. Here's where it appears. Let's look a little more closely at this. The electron beam comes in here, and its principal velocity is in this direction. And as it sees the magnetic field, it experiences a force perpendicular to the magnetic field, which is up and down, perpendicular to the velocity vector like this. And so it undergoes a back and forth oscillation in the plane between the two magnet rays. And this is organized acceleration back and forth, and it produces radiation, sine waves. So far, what we're looking at is very much the kind of undulator that you see in ordinary synchrotrons. The X-ray laser differs from it in that as the electron pulse moves through the array of magnets, it breaks up into so-called microbunches like this. And the distance between the microbunches in the coordinate system of the microbunches you're flying along is one period of the magnets. So the result of this breaking up into microbunches is that the waves emitted by the various bunches of electrons in the bunch become coherent and superimposed. And you get a much higher power density because they all radiate in phase. Let me take a second to tell you why these break up into microbunches. Because the electron is undergoing this sinusoidal motion back and forth, there's a small velocity component in this direction. In the plane of the magnets back and forth. So if we ask, there's a velocity going in that way, there's a magnetic field going this way. The force on the electrons is then exerted along the direction of motion. And so the electrons are pushed back or forth until they reach a place where they're experiencing no net force on them. And those represent the different microbunches in this larger bunch of electrons. So when people started thinking about having such powerful pulses, one of the first questions was, will you blow up your specimen before you can do anything useful with it? This is a wonderful simulation which has been borne out quite well in the experiment by Neutze et al. Janos Haigio had a great deal to do with it. And it's a picture of a simulation of lysozyme interacting with an X-ray pulse and showing what happens to the structure. And all the radiation takes place instantaneously within the duration of the pulse. And so it is that the molecule looks really pretty good here, but it rapidly falls apart. So this was a simulation that convinced people that you could really use these X-ray laser type beams and pulses to examine specimens, crystals. This is a slide that I'm actually going to skip. It has to do with all of the different kinds of experiments that are going to be enabled by this, but I don't know how Snell expected to get through this talk. Right, now on to crystallization. So remember, all this was preparation of the wonderful tools we have for crystallization and why it's important to have crystals, and now we're going to see how we do it. Here's his definition of crystallization. There are three processes involved. Nucleation is the creation of a small handful of molecules arranged in an orderly way onto which molecules can add. Transport means that when the nucleus forms, there are molecules nearby that will diffuse over to it and help it grow, and growth means growth. The slowest aspect controls growth and size. Characteristically, that's not nucleation, but not always. So, I'm going to talk about some of the practical aspects of crystallization and look at some of the different kinds of experiments. And crystallization of small molecules was studied long before proteins, and there's a lot of theory about it. There are often two-component systems, water and something. Macromolecules are harder. They have water, detergent. There are often cofactors in there. And there are issues of order and disorder within the specimen that are not characteristic of small molecules. You don't often find a denatured skin of denatured protein when you're trying to crystallize sodium chloride. This is a diagram that will appear in many forms throughout the rest of the talk. This is the concentration of the macromolecule. This is the concentration of the stuff you add to make it come out a solution, precipitating agent. Up here in the far left, we have a lot of high molecular concentration, high precipitation concentration, and everything crashes out. The nucleation zone is a zone in which the concentration and the macromolecular concentration, the precipitant concentration, are sufficient to produce small crystal nuclei. It's a critical point that it's usually harder to make a nucleus than it is to grow it once you've made it. There are entropic effects that bring small numbers of molecules together and other effects that make a free energy barrier. This is a zone over here in which nuclei will not form but will grow. So the dotted lines in this picture illustrate the trajectories across this phase diagram of various kinds of crystallization experiments. The experiment called batch means that you take a solution of protein and you dump it in the precipitating agent suddenly all at once. And so it starts over here in the nucleation zone, if you're lucky, and gradually follows this path out here. If you look at something like dialysis, what you're going to do is have a protein solution in which precipitant gradually dialyzes in. So this is a path over time. And again, if you're lucky, you start to form nuclei, and then they can, the macromolecular concentration, this is the concentration-free solution. It declines when you form nuclei and you go through the metastable zone. You can trace the other ones as well. These are some of the classic ways in which experimentalists have chosen to adjust the concentration of precipitating agent in these experiments. Joe, if I say anything horribly wrong, will you just stand up and yell at me? Microbatch is basically an experiment in which there are small wells in which you mix protein and precipitating agent, and you cover it with some kind of a vapor block, in this case paraffin oil, so that you don't get a lot of diffusion out of these little wells. Diffusion is a big problem if you have really small volumes, and you have to be careful not to let everything disappear before you finish. Vapor diffusion involves an equilibrium between two solutions, one of which is usually the precipitating solution. The other one is a solution having a protein in it, and water or buffer, if it's a volatile buffer, will move from the area of higher buffer concentration to lower and will make its way into the protein drop. And this is a hanging drop. So this drop over here is protein plus a little buffer. And the precipitating agent is here, and the water will diffuse out of the protein drop into the precipitating agent, concentrating the drop. And these are two other versions of the same experiment in which water diffuses out of the drop into the larger container. These are two versions of dialysis in which you have a semi-permeable membrane that provides a blockage for the protein but allows liquids or salts to move into the protein solution or out. And this is a little tube, and this is a very clever device called a dialysis button that puts small volumes. This is Eddie's picture of, again, how these various experiments will produce, ideally, a crystallization of crystal. And how, and again, if you follow dialysis along, the precipitant concentration rises. It gets to a point here where in the nucleation zone, it forms macromolecular concentration declines. You get into the metastable zone where you couldn't form nuclei, but the crystals can still grow. If you put in all the trajectories that happen to miss in an experimental way, the slide will be full of dotted lines going to different places. This is the ideal case, remember. So I'm just going to go through these. So this is a blow-up of a very simple phase diagram for crystallization. Again, you start out with a batch experiment, which you put the precipitating agent in right away. And because you tried a whole bunch of different things, some of those circles would have been here and here and here, but one of them is here in the middle of the nucleation zone, and it forms nuclei, passes through the metastable zone, where you make crystals. This is a picture to show you the region that you sometimes explore in a complicated crystallization experiment. It falls far outside this phase diagram because you don't know it for each protein. You notice conveniently there are no numbers on the axes. And over here what we have is functions of the macromolecular concentration, the precipitant concentration, because these things are not linear, and they define the kind of space that one might have to explore to actually find these little regions. So this is a kind of written summary that's a little dense, but let's look at it for a minute. There are distinct thermodynamically defined zones where the conditions determine the phase of protein. Undersaturated, saturated, metastable, labile, and precipitation. And again, I think we should skip here to the two most relevant zones of crystallization, metastable and labile. You drive a protein to the labile zone that is highly supersaturated, where the protein undergoes spontaneous homogeneous nucleation. Homogeneous nucleation means it nucleates itself. Once the nuclei form, the level of supersaturation can be decreased to the metastable zone that allows crystal growth. The metastable zone is thermodynamically supersaturated, but it takes a very long time for anything to happen. The precipitation zone, which is the upper right on our diagrams, is too supersaturated to support anything except rapid precipitation. Eddie is pointing out here that the phase diagram is really multidimensional. It's a function of temperature. It's a function of additives of various kinds in addition to primary precipitating agents. Key message: crystals form under solution conditions that fall between those producing clear drops and those producing precipitate. And that path that we saw for, here again, for many different mechanisms illustrates that. You end up here, where the crystals grow, and there are various paths into the nucleation zone and then out. Clear drops are here. This is a wonderful slide, I think. It shows you a lot of the different things that you observe experimentally. There are 10 different kinds of drops. This one is clear. This is one that has crap in it. And then there are other ones that all contain clues. Item 2 shows phase separation, something that's in the part of the talk that we probably won't get to, but you end up with liquid phase separations, and there are high protein concentration droplets surrounded by low protein concentration solution. This is phase separation and precipitation. This is a skin that I told you about that often arises from denatured proteins. Sometimes you have to peel it off to see what's going on. This is phase separation with crystals. 6 is, there's 6. I don't know what 6 is. 7 is precipitating skin. 9, we have to go to something good. Crystal. This is the best. Okay. So you're on track. So I have 5 minutes left in this talk, which had 92 slides in it. Snell was going to talk a lot faster than I'm capable of doing. So I would like to skip a lot of this and go to a tiny bit of his description of theory. And spend maybe 5 minutes going through some of these things. Here's the definition of crystallization again. Here are the processes that go on. Here is a statement about the kinetics. Here's a little picture. This is the nucleus. It's an interesting question how big the nuclei for protein crystal growth are. I don't think there's really a lot of literature on it. Characteristically, in many systems, there is when you have a nucleation growth phase, there's a relationship between the time it takes to form the nucleus and the size of the nucleus. And there are plots that allow you to figure out how many molecules there are or elements there are in the nucleus based on the plot of the log of the delay time versus the log of the concentration. This, I think, is a picture of how the nucleus is a very dynamic structure. Nucleation is a first-order phase transition. Comes from density fluctuations, then overcomes a free energy barrier. The barrier has many terms in it, including it's very expensive to have surface, you have no volume, and there are entropy effects that are quite expensive when you have to order everything pulling out of solution. This is a picture of the width of the metastable zone, where we would like to be, and this is the nucleation frequency. That was way up. When you get to the right level of supersaturation. This is a plot of the free energy terms that go into creating a nucleus. This is the surface energy contribution. It's always opposing formation of crystals, and that's because solvent competes with protein molecules for binding sites on proteins. So if you want to make a protein-protein contact in a crystal, that molecule has to be desolvated in order to make a protein-protein contact. The molecules on the surface are not being desolvated. They're, in fact, being pulled away. Volume and energy contributions are protein-protein contacts and other elements within the volume. And when you add these two together, if you can do the calculation with some accuracy, you get to see something about the nucleation barrier. This is, of course, the size of the cluster that we're looking to form. So the theory about nucleation and growth is quite well developed in a kind of abstract way, and it fits simple cases quite well. But it's not, it's the kind of thing that can be changed dramatically by the addition of a second ion or other components to the crystallization medium. So the 45 minutes that are on the program for this have gone. And I apologize to you for not being better organized. And I think that I'm just going to stop. I don't really think I can get through the rest of this long talk. I wish I'd had a little more time to go through it and filter it. But I walked in at 8:30 to find that Snell was in Dulles. So I thank you for your attention. I'm happy to take questions. I think Joe Luft will help me take questions. And again, have fun.